Okay. So today I'm going to talk to you about the development of synthetic methods using isoindole chemistry. Okay, why is this not working? Okay. First, I'm going to give an introduction to isoindoles and isoindole reactivity. Then I'm going to discuss a review of the recent literature on isoindole chemistry that I will be submitting. And then I will talk to you guys about a one-pot synthesis of polycyclic isoindolines using isoindole umpalung. And then I will describe my efforts towards the development of two cascade reactions using isoindole chemistry. And finally, I will give some acknowledgements and then take your questions. So first, what are isoindoles? Well, isoindoles have the structure shown at the top left, structure number 1. They're aromatic heterocycles that consist of a benzene ring, which is shown in blue, fused to a pyrrole ring, which is shown in pink. They have 10 pi electrons, which I was going to point out, but I forgot my laser pointer. Sorry about that. And then there are two isoindole tautomers, which you can see in the middle there, the 1H isoindole tautomer and the 2H isoindole tautomer. A laser pointer and zoom. Okay, wait, that just skipped the slide. Oh, nice. Okay, they can see my cursor. So they're the 2, 4, 6, 8, 10 pi electrons. And then here are the isoindole tautomers that I had just started mentioning. And the 2H isoindole tautomer, which is this one here, is the one that typically predominates, and that is because it's more stable due to its higher resonance energy. So when I say isoindole, from now on, I'm referring to the 2H tautomer. Isoindoles are pi excessive in nature because they have 10 pi electrons per 9 atoms, which works out to an electron density of more than 1 pi electron per carbon atom. And for this reason, they often behave as nucleophiles. Isoindole derivatives, such as the one shown down here at the bottom, are ubiquitous in nature and in biologically active compounds. And here are some examples. In the top row, we have some examples of said biologically active compounds. First up here, we have navaxamide, which is an anti-cancer drug candidate, and it contains an isoindoline ring. Second, we have apremilast, which is an anti-inflammatory drug, and it contains a thalidomide. And then on the far right, we have these broad spectrum antibacterial agents, and they contain an isoindolinone. Then on the bottom, we have two natural products, and both of those also contain an isoindolinone, and they're also biologically active. Isoindoles are nucleophilic at the alpha position, and we can see this by drawing resonance structures. In structure 1A, which is this one here, there's a negative charge on one of the alpha carbons, and so that would be the nucleophilic alpha carbon. While structures 1B through 1D also have a negative charge, but it's on other carbons, only nucleophilic reactivity at the alpha carbon forms a complete benzenoid ring. And a complete benzenoid ring is more stable than just a pyrroloid ring or no aromaticity at all. So like I said, I'm in the process of submitting a literature review on the synthesis and reactions of isoindoles from the past decade. And now I want to highlight a few of the methods and approaches that will be discussed in that review. And I will focus specifically on the 2H isoindole tautomer. So first up, we have condensation reactions, which can be used to synthesize isoindoles. Condensation reactions are reactions that are accompanied by the loss of a small molecule. And in these reactions that I'm going to be discussing, that molecule is water. Condensations that are used to make isoindoles typically involve the reaction of a primary amine with an orthodisubstituted benzene that has 2 electrophilic sites. Generally, these electrophilic centers are one of 2 types. You can have an aldehyde or a ketone, that's type 1, and then type 2 is a bromomethyl group. Structures 14A and 16A are the two most commonly used dielectrophiles in these reactions. 14A has one of each type of electrophilic center, and 16A has two aldehydes. Reactions of orthothialdehyde require a reducing agent because orthothialdehyde must undergo a 2-electron reduction to get to the isoindole, at least for C-unsubstituted isoindoles. But reactions of 14A, on the other hand, require no redox chemistry. A key feature of the mechanism for these reactions is that they pass through an iminium intermediate, which on here is structure number 19, and that is subsequently deprotonated to form the isoindole, which is number 15. Some recent examples of these types of reactions can be seen here. And if you'll notice, this is also how we prepared isoindoles. Our approach is very similar to those of Voitenko and Sievchenko, with the key difference being that they used 2 equivalents of the primary amine. And the reason they did this is because one will act as a base and deprotonate the iminium intermediate that I just showed you to form the isoindole. And instead of using 2 equivalents, we used triethylamine instead as an additive because it's basic, cheap, and it's easier to remove. So next up, isoindoles can also be synthesized from isoindolines, which is one of the derivatives I showed you on the first slide. In this reaction, the isoindoline is oxidized to the isoindole by the oxygen found in the air via a light catalyzed reaction. The isoindole then goes on to act as an electron-sufficient diene in a Diels-Alder cycloaddition reaction. Isoindoles can also be made from the reduction of isoindolinones, such as in this hydrosilylation example. In this reaction, the alkoxide activates the silane and facilitates hydride transfer to the carbonyl. And this gives silohemiaminal intermediate 32. And then subsequent elimination results in the loss of the siloxy moiety, which gives the isoindole. So I already mentioned that isoindoles commonly act as nucleophiles, and this is a recent example of that. In this example, Yegorova et al. Installed amides and thioamides at the alpha position using isocyanates and isothiocyanates, respectively. This is one of many examples of an electrophilic aromatic substitution reaction of isoindoles. And this brings us to the first project that I'm going to present, which is a one-pot synthesis of polycyclic isoindolines using isoindoumpelung. Umpelung is a German word which means the reversal of polarity. And there are so many examples in which isoindoles serve as nucleophiles, such as these two here at the top, which are examples of electrophilic aromatic substitution reactions. So we thought, what if we could expand their reactivity and use them as electrophiles instead? For the same reason that isoindoles are nucleophilic at the alpha position, they are also basic at the alpha position. And so protonation at the alpha position gives an iminium, and iminiums are good electrophiles. By the way, an isoindole iminium is called an isoindolium, since I will likely end up using that term. So one reaction that uses an iminium intermediate is the Pictet-Spengler, an iminium electrophile, is the Pictet-Spengler reaction. In this reaction, an iminium is formed in situ from either an aldehyde or a ketone, an amine, and protic acid. So the aldehyde or ketone is there. Sorry if that sounded like 4 things, but it was supposed to be 3. So after it forms the iminium, the aromatic ring then does a nucleophilic attack on the iminium electrophile, resulting in cyclization. And then subsequent rearomatization gives an isoquinoline product. So great, we thought we'll extend the Pictet-Spengler reaction to isoindoles. There's just one problem. And that is that due to their nucleophilic nature, anytime an isoindole nucleophile and an isoindolium electrophile are present at the same time, the isoindole will attack the iminium. And this results in polymerization. As you can see, there's this dimer here. But we reasoned that this could be avoided if we can ensure full conversion of the isoindole to the isoindolium. We figured that by using a sufficiently large excess of protic acid, we could completely convert the isoindole to the isoindolium. And that if we use a significantly lower concentration during cyclization, we could disfavor the intermolecular polymerization reaction and promote the intramolecular cyclization reaction. We wanted to validate our hypothesis that the isoindole could be fully converted to an isoindolium using a large excess of protic acid. So we chose TFA as our acid for our model system because it's one of the milder acids that's been used successfully in Pictet-Spengler reactions. We chose a simple alkylamine for the primary amine reacting partner because we intended to use proton NMR spectra to validate our hypothesis. And so we wanted something that would give simple spectra with the only aromatic signals coming from the isoindole and the isoindolium. We started with a stepwise procedure in which we isolated and subjected the isoindole to an aqueous workup for a cleaner spectrum. I will show the spectra on the next few slides, but since the stepwise procedure was successful, we then tried a one-pot approach to establish that the same results can be achieved via one-pot approach. We wanted to do this because one-pot approaches are often more efficient and higher yielding. There are several pieces of evidence here that support our hypothesis. So first, we have 3 distinct aromatic signals for the isoindole, which is what we would expect because there are 3 chemically distinct protons. And then in the isoindolium here at the bottom, we have these 4 aromatic signals, which is what we would expect for that. And the isoindole has the expected AA prime, BB prime splitting pattern in the aromatic region, and the isoindolium has the expected first order disubstituted splitting pattern in the aromatic region. We also see the appearance of 2 new peaks in the isoindolium spectrum. First, we have this one that I've labeled D, which is at 9.33 ppm. It's a singlet that integrated to 1 proton. That is consistent with an iminium CH. And then at 5.26 ppm, we have another singlet that integrated to 2 protons, and that is consistent with a benzylic CH2, which is consistent with this structure. We also note that the isoindole peaks have disappeared. They're not in the isoindolium spectrum. And so with that, plus the fact that there is no sign of polymerization, like no peaks unaccounted for here, taken together, those things suggest that there is full conversion of the isoindole to the isoindolium. And here's the NMR for the one-pot approach. I apologize that the isoindole is now on the bottom this time, but we can see here that similar results were observed. The same peaks are in each spectrum, plus these additional peaks from triethylammonium, which is to be expected because we did not do a workup to remove it in the one-pot approach. We also see here the disappearance of the isoindole peaks and no sign of polymerization, which shows that full conversion is also possible via a one-pot procedure. So in our envision one-pot approach, what would happen is we would first form an isoindole in situ. That's this guy number 55 there, via a condensation reaction of the aldehyde species 14 with a primary alkylamine using triethylamine as an additive. Next, we would dilute the reaction mixture by adding more solvent, cool it down because acid-base reactions are exothermic, and then we would add a sufficiently large excess of protic acid to form the isoindolium, and then we would let it warm back up. The aryl group would then act as a nucleophile and attack the isoindolium electrophile, which would result in cyclization. Or did I skip? I think, sorry, I skipped the, no, I didn't skip the sufficiently large excess of protic acid. I said that. Yes, and then the aryl group would act as a nucleophile and attack the isoindolium in a Pictet-Spengler type reaction to give the polycyclic isoindolene product. So with one of our central hypotheses confirmed, we just needed to choose a beta aryl ethylamine reacting partner for our model system for the cyclization. One of the earliest Pictet-Spengler examples, I believe it was reported in like it says right there, 1928. Anyway, it's one of the earliest Pictet-Spengler examples used tryptamines, and those are these, number 54A, in place of phenylethylamines. And so we ended up choosing tryptamine for our model system because they're good and well-established Pictet-Spengler substrates. They're biologically relevant, and they are better nucleophiles than phenylethylamines. So first we screened various solvents. The chlorinated solvents all gave good yields, high yields, with DCM giving the highest and DCE a close second. The nonpolar solvent toluene also gave a high yield. However, polar protic and polar aprotic solvents were not suitable for this reaction. Whoops. Okay, here we go. Next, we screen acids of varying strengths, and TFA seemed to hit the sweet spot in terms of acid strength. The stronger acids, HCl and mesic acid, gave significantly lower yields and resulted in complex mixtures. Acids weaker than TFA, so those are the stronger acids. Acids weaker than TFA gave lower yields, and no cyclization was observed at all for acetic acid, which is entry 5. Next, for the number of equivalents, okay, I don't know why it's doing that. For the number of equivalents, we found that the percent yield increases with as we increase the number of equivalents, with 5 equivalents giving a 94% yield for the stepwise procedure. And then we also observed the same trend with a one-pot procedure, except that more acid was required because some of it was inevitably consumed by the residual triethylamine. Next, we optimize, or with our optimized conditions in hand, we then investigated the scope of the amines, starting with substituted tryptamines. We found that substitution of the aryl ring, which is the R1 position, with an electron donating group gave similar yields to the unsubstituted tryptamine. However, using an electron pour, there are animations here. Using an electron pour tryptamine with an electronegative chlorine atom reduced the yield, and the reaction required heat to obtain the best results due to the reduced nucleophilicity of the tryptamine. And then finally, we investigated the effects of N-methyl substitution, which is this R2 position here. And we found that on the other hand, did not significantly decrease the yield. To extend the scope of our reaction beyond tryptamines, we investigated other indole and pyrrole containing substrates due to their biological relevance. The 4-amino-methyl indole, or it's called 4-amino-methyl indole, gave this cyclization product 64 here. And we observed a lower yield for that, likely due to the strained geometry of this product, and heat was also required here to obtain the best results. However, 2 and 3 amino methyl indole did not cyclize even with heating, and the isoindoles were observed following a basic aqueous workup. We suspect that this is possibly due to the strained nature of the 5-membered ring with the double bond, which is there. So we obtained a high yield for pyrrole cyclization product 67. However, that's this one, furan cyclization product 68 down here didn't form, and only the isoindole was obtained. We suspected that our conditions for that one were too mild, as HCl was used as the acid in the literature precedent for Pictet-Spengler reactions of that amine. Finally, we tried some of the seminal Pictet-Spengler phenylethylamine substrates, which are these two there. Oh, sorry, I forgot to change the ordering of 69 and 70. But these are two examples of Pictet-Spengler substrates that we tried. Homopipernylamine was expected to give product 69 here, which is on the bottom right. And dopamine was expected to give product 70 here in the middle on the bottom. However, homopipernylamine did not cyclize, and dopamine gave a complex mixture, and that was, both of those things were even at 80 degrees Celsius. Although perhaps it would have cyclized at higher temperatures or under stronger conditions. Next, we examined the scope of the aldehyde, starting with substitutions on the aryl ring. We investigated substitution with electronegative halogens as well as electron donating groups. We found that substitution of any kind decreased the yield with an orthomethyl group that is these products, giving the greatest decrease in the yield. And this is likely due to a combination of sterics and the aldehyde also being less reactive, less electrophilic. Ortho and meta substitution we found, which is pairing 71 and 72. We found that those gave similar yields, with ortho substitution giving slightly lower yields. The highest regioselectivity was observed with a methyl group in the ortho position, and that was again likely due to sterics. Good regioselectivity was also observed for chlorine in the ortho position, that's back to 71. But meta substitution, on the other hand, resulted in poor regioselectivity, and the regioisomers were not separable. And therefore, the regioisomers were not conclusively identified. But we determined the regioselectivity for the 3-chloroaldehyde cyclization product number 71. And we suspected, based on this NMR data here, this proton NMR data, we suspected that major product was 71A because the chemical shift of the methine proton was upfield of that of the minor regioisomer, which is consistent with it being farther away from the chlorine atom. But we wanted to confirm this, so we used proton-proton NOE data to do that. And we did find that 71A was the major regioisomer. The observed NOEs with the methine proton here, so in other words, the NOEs between this proton and the methine proton and this same proton and the tryptamine NH, since we saw those NOEs, that means there's no chlorine blocking this position right here, which is the one on the aromatic ring that's closest to the methine CH. And so that is consistent with cyclization through the aminium that is meta to the chlorine. So in other words, that would be this intermediate here. There's the aminium, there's the chlorine, so they're meta to each other. So that's consistent with cyclization through that intermediate, which is not stabilized by the chlorine via resonance and is consequently less stable than aminium 76B down here, which is resonance stabilized because the chlorine is in the ortho position there. We also noticed that the reactions that required heat to cyclize appeared to give the opposite regioselectivity based on the chemical shifts of their methine protons. Thus, we concluded that in the absence of heat, the less stable, more reactive iminium leads to the major product. We weren't able to get aldehydes with substituents at the benzylic position to cyclize, which we suspected was probably due to sterics. So we decided to use them to probe the regioselectivity of isoindolium formation. So we found that only the more stable, more substituted isoindolium was observed via proton NMR, when that's 78A. And this confirmed our suspicions about the steric hindrance. And here is the proton NMR for 78, and it is consistent with structure 78A. So we have the singlet here at 2.24 ppm that I've labeled as A, that integrates to 3 protons, and that is consistent with a methyl group that has no neighboring hydrogens. We also have this singlet here at 5.15 ppm, which I've labeled as B, that integrates to 2 protons, and that is consistent with a benzylic CH2 with no neighboring protons. Finally, we investigated substituted combinations, or actually combinations of substituted aldehydes with amines other than tryptamine. And we found that reactions of the 3-chloroaldehyde, which is the one with the chlorine ortho, we found that reactions of that aldehyde with other amines tended to give higher yields but lower selectivities, and that's likely due to the increased reactivity of the aldehyde. However, unfortunately, the reaction of the 4-chloroaldehyde with pyrrole, the pyrrole amine substrate, still gave, and that's product 82, product mixture 82, that still gave an inseparable mixture of regioisomers. So with that work completed, our next goal was to extend our iso-indo-Oompa-Lung approach to other nucleophiles. And one possibility that we came up with would be to use amine nucleophiles. And so that would entail using diamines as the amine reacting partners. We anticipated that the second amino group would be incompatible with protic acid, but we hypothesized that the isoindolium could still form without acid because of the equilibrium with the isoindole. We chose 87A as the diamine for our model system because it could be used to access analogs of compounds with a variety of important biological activities, which I will come back to in a couple of slides. We also wanted to use a non-symmetrical diamine that was easily modifiable because that would add regioselectivity and interest to the reaction. However, when we tried our model reaction, we observed a low yield, and we suspect that is because the product is unstable because it forms reversibly. The reaction also suffered from side reactions, so that was another issue there. And one of the side products that we observed was this oxidation product number 92A, which is likely formed via aerobic oxidation. We were particularly excited by this product because it is more similar to the biologically active compounds that I said I will come back to, and that's because it has an amidine functional group. So in our envisioned approach, we would form the cyclization products from the isoindole and then oxidize them in situ. In addition to the major regioisomers shown on the previous slide, which comes from the more nucleophilic benzylamino group forming the isoindole and the less nucleophilic aniline amino group cyclizing, we would also get a minor regioisomer from the aniline forming the isoindole instead. And that is this one, 92B there. So these are on the right here, these are the biologically active analogs that I referenced earlier. I highlighted the key structural features of these compounds and my targets, the ones that they have in common. But as you can see, batracillin, which is right here, number 93, and tryptanthan, which is here, number 94, those are the most similar to our major product, which is here on the left, 92A. And these indolo, indolo 1,2-C quinazoline, which is the scaffold, that is most similar to our minor product, which is 92B up there. These analogs have a slew of interesting biological activities, which you can see on the left, but most notably, tryptanthan has activity against coronaviruses and shows promise as a potential antiviral for treating COVID. So to investigate our planned approach, we screened oxidants and we found that N-sulfonyl oxaziridine number 96 worked the best. So N-sulfonyl oxaziridines are electrophilic, and in this mechanism proposed by Davis for the Davis oxidation of enolates using N-sulfonyl oxaziridines, the nucleophilic enolate, which is number 98 here, attacks the oxaziridine oxygen to give intermediate number 99. And then that tetrahedral intermediate collapses, kicking off the anionic salt of an alpha hydroxy ketone, that's number 100 here, plus the N-sulfonyl imine byproduct. In our reaction, the nucleophile is either one of the amines in the cyclization product, or could also possibly be the isoindole. So next, we optimized the conditions, and we found that increasing the number of equivalents of the oxidant to 1.5 gave the best results. However, increasing the number of equivalents further decreased the yield. We also found that shortening the reaction time to 2 hours gave optimal results, and that cooling hindered the reaction. So with our optimized conditions in hand, we then investigated the scope of the diamine reacting partner, starting with aryl 1,2 and 1,3 diamines. While 92A, which is a 1,3 diamine, and that's our model reactant, while that one worked well, the 1,2 diamine number 102, or that gives product 102, that would be 87B, be the diamine. That one did not work well. It gave a complex mixture, perhaps because of the strained nature of the cyclization product, the decreased nucleophilicity of the aniline, and also the fact that the isoindole formed incompletely. Next, we invested alkyl 1,2, 1,3, and 1,4 diamines, and we found that diamine number 103A, which is 1,3 diamine, gave moderate yields after purification by preparative HPLC. However, a basic aqueous workup and lyophilization were needed to remove all of the DIEA and DIEA HBr salts. And we investigated the dihydrochloride salt of diamine 103B, which is a 1,4 diamine, and that gave 0% conversion to the isoindole with up to 7.2 equivalents of DIEA. Perhaps a stronger base would be needed to deprotonate the salt. Then we investigated an electron poor 1,2 diamine, which is number 103C, and that one gave only trace yield. we suspect that that one was not nucleophilic enough to cyclize. I won't discuss this slide because this work was done by my colleague Yuhang Zhao, but I wanted to show it because it will become relevant later on. So we wanted to find a way to make our targets without using redox chemistry because we found that our oxidizing agent was unstable. So instead, what we decided to do is we decided to use orthothialdehyde as the dielectrophile because there is no redox in the conversion from that to the product. And we discovered that essentially the same reaction had been reported by Troschutz, but under acidic conditions and with the opposite regioselectivity. And that is because that under those acidic conditions, the less basic aniline will be the last to get protonated by the acid, and its ammonium will be the first to get deprotonated back to the free amine, which is what will react with orthothialdehyde. Troschutz did not investigate modifications of the aldehyde, and with the exception of the unsubstituted 2-amino-benzylamine, all the diamines used in that paper had a benzoic substituent. They also used an extremely large excess of acid. I think it was about, I calculated it, I think it was like 140 equivalents, but amounting to something over 100 equivalents. And we decided to investigate conditions for obtaining the opposite regioselectivity and also filling in the gaps in Troschutz's approach. So first we decided to screen additives. And we found that an amine base as an additive had inconsistent effects. Using an amine base as an additive had an inconsistent effect on the yields and also the regioselectivities. So we opted not to use one going forward. However, we were able to improve upon Troschutz's results by using only 0.55 equivalents of TFA in DCM. Of all of the solvents investigated, we found that methanol gave the best combination of a good yield and high selectivity. And we suspect that this is because it acts as a proton source and therefore facilitates proton transfers. So at room temperature, we found that a 48-hour reaction time gave a high yield and the best selectivity, and that increasing the temperature to 55 degrees Celsius allowed us to decrease the reaction time to 15 minutes with good regioselectivity. So next we invested the scope of the orthothialdehyde reacting partner, and these are all predicted structures, and further work would be needed to conclusively determine the structures of the regioisomers. But we investigated two aryl substitutions. First up, the 4-chloro-orthothialdehyde substrate, which would give product mixture number 112. We found that decreased the yield, but the yield was still good, and that 3 of the 4 possible regioisomers formed. We also tried the 3,4-dichloro-orthothialdehyde, which would give products number 113, or gave products number 113, and that one significantly decreased the yield. But as expected, we observed both of the 2 expected regioisomers, and the regioselectivity was similar to the unsubstituted. We also investigated the effect of benzylic substitution with a methyl group, which would give product mixture number 114. And a moderate yield was obtained for that one. And only 2 products were observed. We have suspected product 114A was the major product, followed by suspected product number 114C, which forms via cyclization at the opposite benzylic position. Notably, suspected product number 114B was not observed. My colleague, Yuhang Zhao, also obtained the same major product via the cyclization oxidation cascade, except he did observe 114B as well as a minor product. Next, we investigated substitution of the diamine with a chlorine atom, which would give product mixture number 115, and that gave a moderate yield and lower regioselectivity. We also investigated the combination of the 4-chloroorthothaldehyde plus the chlorinated diamine, which would give product mixture number 116. We found that the yield was similar to a combination of unsubstituted orthothaldehyde plus the chlorinated diamine, but slightly higher. And that was because of the aldehyde being more electrophilic. As with the combination of 4-chloroorthothaldehyde plus the unsubstituted diamine, 3 regioisomers formed at 55 degrees Celsius. However, we also tried this at room temperature and we got only 2 regioisomers. And for the major products, the regioselectivity was the opposite of at 55 degrees Celsius. And that's with respect to the chlorine on the isoindolene arrow ring. So with that said, as far as the potential for future work and future directions go, we could, or we would need to expand the substrate scopes of the reacting partners, conclusively identify the structures of the regioisomers, and then we could screen for some of the biological activities of the structural analogs that I referenced earlier, particularly activity against COVID-19. So with that being said, I have some acknowledgements to give. First, I would like to thank Professor Shang Wang, my advisor. He's given me a lot of guidance and taught me a lot. And I greatly appreciate that. And I also greatly appreciate him putting up with sitting through my practice talk. So thank you for that. And then I would also like to thank my committee members. Professor Tarek Samakia, who's here in person, has also given me a lot of guidance, which I greatly appreciate, as well as for agreeing to serve on my committee. And thank you to the rest of my committee members, Professor David Walba and Professor Michael Marshak, and Dr. Patrick Dorner-Barber. Thank you to you guys as well for agreeing to serve on my committee and doing everything that that entails. I'd also like to thank some of the former Wang Lab members, are the ones that I worked with anyway. Yuhang Zhao, Xinfeng Wang, they were postdocs. They were super helpful to me, particularly in training me to use the preparative HPLC. And Justin Olson and Sarah Robertson as well. I would also like to thank my undergraduate advisor, Professor Catherine Thomas. Not only was she a great professor, but one thing that she did that has really improved my life is she taught me how to have the confidence to do certain things myself or do lots of things myself, I should say. And thanks to her, I now attempt to fix all my appliances. I build my own computers. I wax my own skis and things of that nature. So thank you for that and for all of your guidance as well. And then I would also like to thank the Ohio Wesleyan University Chemistry Department of the rest of the Ohio Wesleyan University Chemistry Department from 2005 to 2009, which includes Professors Heather Grunkemeyer, Dan Vott, Dale Brew, David Lever, and the late Professor Kim Lance. They were all exceptional professors, and they are part of the reason I'm here now. And then I would also like to thank Dr. Tracy Casalt. She's one of the kindest, most compassionate people I've had the pleasure of meeting, and she's just been super helpful and supportive to me. So thank you for that. And then I would also like to thank Tim Minger and Tiani Yang. They're both also PhDs. They are my wildlife photography buddies. Yeah, thank you to you guys as well for helping keep me sane. And I'd also like to thank the Gen Chem teaching crew. Rachel is here with me in person, but Rachel, Felicia, Star, and Chris. You guys were super helpful to me while I was teaching 3 courses during my final semester, and you guys are just great people, so I greatly appreciate you. And then I would also like to thank my family. My mom's here, and then my dad and my brother are here virtually, and as well as my aunts and uncle. I would like to thank all of you guys. You guys have been super supportive, so thank you. And then finally, all of my other friends who I didn't mention, and I made this collage for everyone. I would especially like to point out that my friend Tiani loves to take pictures of my friend Tim, and he likes to take pictures of our backs. So I have several photos of our backs on there. But so thank you again. And with that, I'd like to ask, does anybody from the audience have any questions?
Well, before anyone start asking questions, I'd like to say a few words about Rachel, because I was supposed to give her the introduction before you start your presentation. Somehow we skipped that part. All right. So Rachel, I guess, started at CU in 2015, right? Yeah, and she joined my research lab in 2018, well, in the summer, after a sudden leave of her former advisor. So she has only been working in the lab for about 3 years. And the ISO-Indo project was actually our first paper published on this topic. So it was a brand new area we started back in 2017, 2018. So that was actually a great achievement, because we used to work on a very different type of chemistry, the Indo chemistry. And so she helped us to make a good transition into the new regime. And over the years, I think, as you have seen from her presentation, Rachel has become a very serious and capable synthetic chemist. And she is very detail-oriented researcher and with very critical thinking about both literature and her own work. And so perhaps she's the sometimes too critical on her own results. So she spent a lot of time repeating, optimizing her own experiments. And one thing you may not know is, I think she didn't mention, was that most of her compounds were not very easy to deal with. And the purification usually takes a lot of efforts. And she did try a lot of different approaches to purify and characterize her products. So those were very time consuming. So I think that's pretty much what I want to say about Rachel. And I think she has become a very capable researcher. And so I'm sure she will be able to take on any difficult topic in her future and develop a successful career. All right. So now we'll take some questions from the audience that are non-committee members. Any questions?
Hey, Rachel, I got a question for you.
Okay.
Why were the cycle-sized isoindolenones, why are those unstable?
The isoindolenones were which do you know which slide number?
I do not, but it was closer to the end. I think you spent the most time on that particular slide.
You mean, I guess just tell me like when I.
No, you were just on it actually.
I was.
Yep.
Is it this one or the other one?
Yes. Which showed a mixture of 113A-B and cyclized isoindolenones were not stable to purify.
I believe that was because they were getting oh, I see what you're saying. Yeah, they formed isoindolenone side products. So it actually wasn't the isoindolenones that weren't stable. Those are actually pretty stable. It's that the desired products were unstable to oxidation, as evidenced by the fact that I observed those isoindolenones by proton NMR.
Okay, thank you.
Mm-hmm. Anybody else?
You went through the oxidant screen very quickly. Would you mind going back to that slide? I just wanted to look at the table again to see the different reagents you tried. Because I've had to screen oxidants before. It's about as fun as doing your own dental work.
Yes.
And I also found it interesting. So it was that, so the Davis reagent that was ultimately successful. When you say your oxidant was O2, is that ambient air or were you bubbling?
It's
O2?
an oxygen balloon.
Okay,
So an oxygen atmosphere.
Okay, so that was actually worse than the ambient air from the conditions that incidentally revealed that you got the dehydrogenation.
Yes, that is correct. And that was something that was perplexing to us as well, because so the model system wasn't run open to air, but we used solvent from the purification system, which is under argon. However, we didn't use an argon balloon with that, for instance. So presumably the oxidant in that would be air. But yeah, there was no reaction with O2.
And so did you ever run the reaction when you saw the 92A appear and you hypothesized it was ambient air? You said that was run with under argon, the reaction was?
No, so that we have a solvent purification system and we have it hooked up to an argon tank.
Gotcha.
And we obtained it directly from the solvent purification system
Okay.
before using it. So it's not like we were just letting it sit open to air and there's a huge amount of air exposure, but we also didn't have an inert gas line going in.
So it's under a sealed septum.
Yeah,
under
vial,
its own pressure.
essentially.
Gotcha.
Yeah.
Did you ever try running it as open to the air, no septum?
We did. I don't believe so. No.
Gotcha.
And I also
Okay.
thought we probably should have tried bubbling O2 through as well. That probably would have worked better.
It can be pretty destructive too. So you found a
Yeah.
reason that works, and that's the important thing.
Yeah.
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 But since you can open this can of worms, I'm supposed to wait because I can't wait. So did you see the oxidized product by TLC before? By TLC, or did you see it after purification before you go to the oven purifier? In other words, could it be that, so at least I saw this chemistry that's alluded to, is that the oxidation happens in silica gel, or alumina will add to the oxidant.
So we actually saw that by LCMS.
The LCMS was on the food reaction part.
Yes.
Okay, I'll ask the rest of the oxidation questions. I just wanted to address that. That's what people say.
Yeah, I was thinking of that, and I was thinking of some of the other dehydrogenation stuff we tried to do with the first BPX route, where we would try DDQ and stuff like that. And it struck me because this is, akin to it. I guess it is a dehydrogenation. We're not saying the hydrogenated precursor to 92A. But that's interesting. But ultimately, it was the Davis reagent for it.
It was actually 96. The Davis reagent. Well, the Davis reagent did give a little bit of product.
Oh
but
yeah,
yeah.
I see. Yeah, 96 gave me 42% yield in that specific. Okay.
Yeah, I mean, a 96 is technically also a Davis reagent, but it's not the Davis reagent. So.
One last question.
Uh-huh.
Leave it. So the hydrogenated precursor to 92A. Did you ever do any 2D TLC on that?
I don't believe so.
Okay. I'm just wondering how. I don't know, because like I said, what we see, some of our cleanest oxidations are just done with the solid phase, stirred, suspended, and open to the air. And I was just, and it's something about co-adsorbing oxygen and the starting material, it increases the effective concentration.
Interesting.
So I was just wondering if you knew its chromatic. But you found an oxidation reaction, I guess, in the end.
Yeah, that one, I mean, we did also monitor it by TLC, but we largely used LCMS, and that one we just figured reason that it was unstable because there were like a lot of things present in the LCMS for that one.
Rachel, when you use like strong oxidants, like entry 3 to 7, did you observe any oxidation of the anilines?
I don't recall observing any oxidation of the anilines. That one, but that probably wouldn't have shown up by LCMS because I think it's too small. So I can't remember off the top of my head whether we did or not for that. I assume you just mean just the oxidized. I mean, I did check. So I did check the starting material though to make sure that it was still good and was not oxidized. I checked that by NMR and it was mostly good. I mean, I would estimate it was probably 95% pure. Oh, Siri thinks I'm talking to her. Okay.
All right, so if there are no more questions from the audience, we will move on to the next session, the closed session. So if you're not the committee members, please leave and we'll talk to Rachel privately. Okay.